Yeah, I'll just give a small introduction, short disclaimer. I have a stutter, so my speech is not as fluent as I'd like it to be, especially in foreign languages. So I hope you can bear with me at the length of my presentation. So I prepared lots of slides, but depending on my speech, I will see like how far I will get, but I might need to have to skip over things. Anyway, thanks a lot for John Hopkins for the support, and like big thanks to Sam and Ted for inviting me and making this amazing conference happen. It's such a pleasure to meet you in person finally. It's amazing. I really enjoy that. So quickly about me, I'm Christof. I'm actually I'm a freelance composer. I have been I think 10 years or 15 years. And I got into PD in my mid-20s after I've studied classical composition, and I had an introductory course in PD. So it was the first time I saw PD actually. And then I went to Switzerland for half a year, and there I took a whole course in PD, and where I really got to learn it and build my first live electronics stuff, and like my own instruments, and wrote a small ensemble piece with electronics. And then I came back to Graz, and I did a theater project where I used PD, and I've been using it since then. So I think since 2015 or so, for lots of my own art and also in theater productions. So it's a really helpful tool. And I studied at the IM in Graz, which is a place that is very important for PD. Like it hosts lots of the infrastructure, and one very important contributor, Johannes Zmölnik, actually teaches there, and he's responsible for the IM infrastructure as well. And so I got to meet him there, and then I rather quickly became involved in PD development as well. I have been programming in my early childhood, and then I abandoned it for piano and cello and guitar. And then only, in my mid-20s, I picked up C and had this background knowledge in the back of my head. So I knew what a variable is, what a loop is. And I started from there. And I think the first thing I actually did in PD was to fix the Windows build system, because back then you couldn't build PD on Windows. So Miller, Bucket, the creator and main developer, had his own private build script with hard-coded paths of his computer. And so he did all the Windows builds, and nobody else could actually build it, because we're using auto tools, unfortunately, I have to say. And this it's not designed for Windows in mind. So I really had to fix it, and then I could finally build PD for Windows, and that was like when I could finally also start developing it, because I've been using Windows. I'm still using it, and I'm also using Linux from time to time. But yeah, some research just I kept using Windows. So how did I come to SuperCollider then? So the thing is that when I graduated from the IM in 2018, I think, Hannes approached me about there's this amazing plugin suite. I think you might have heard about that. And the Amazonic plugins are really great. So here's a little plug for the plugins. And Hannes basically told me, yeah, there's some money in a project, and so if I would be interested in porting those plugins to PD and maybe also SuperCollider. And then we thought, yeah, well, I think we have to factor out all the code and turn it into C++ library, but it's all deeply entangled with choose code. So I don't know if it's really it really works. And so what about I just write a VST plugin host instead? And I thought, yeah, I think it could be useful for a few other things as well. So I said, yeah, let's do that. So I developed a VST plugin extension. So this is the original reason why I did this. I got some money from the IM, and I finished the PD version pretty quickly. I mean, in PD it's really easy to do. It's just method calls basically. I mean, I had to figure out the VST wrapper, but I'd like the actual the PD bindings themselves are rather trivial. And then he like asked, yeah, can you do the SuperCollider version? And in my big naivety, I said, yeah, sure. How hard can it be? And it turns out very, very hard. So I really bit my teeth on that one. I remember I was sitting in a long flight to Japan and had my laptop and the server code trying to figure out the plugin API, and I was basically horrified when I realized, oh, so then there are no direct method calls. I actually have to send messages from the client to the server, and then but I can't really get things back, or maybe I can. I will do it, and then I have to synchronize all the state, like also on the client. Ooh. So this gave me big headaches. In the end, it turned out that it's doable. So the extension works, and I think it works fairly well. There are no major complaints as far as I'm aware. But if you look at the implementation, compare the PD side and the SuperCollider side, I think you will see what I'm talking about. So and that was also the reason. So I had to study the server code pretty closely, both as a synth and Supernova, and also the class library to actually make the language wrapper. And then I discovered, okay, there actually I'm using parts of the API that haven't really been used, and there have been some bugs in as a synth. And it turns out that some parts of the API I needed hasn't been implemented in Supernova at all. So the functions were literally empty. So I had to implement it for Supernova. On the way, I discovered a couple of bugs in Supernova and fixed those. And that's how I got started in development. And I've been like, I would say, a casual SuperCollider contributor since then. Whenever I find a bug that bothers me or something I need, I do it. But like my main development work is my own software and PD. So the priorities are unfortunately pretty clear in this regard. Yeah. But the thing I want to talk about today is actually I want to give like a cross comparison of PD and SuperCollider, because when I've been using PD, I had a fairly clear concept of what a computer music environment should be. And then when I really learned SuperCollider, lots of these notions have been challenged fundamentally. And that's the thing. If you're just using like one environment, you just you basically live in a little bit of a bubble, and so you don't see other possibilities or ways of doing things. And this goes both ways. When I work with SuperCollider, I was like, okay, these things are really much easier in PD, for example. And hopefully we can learn from each other. That's what I'm trying to do in my development work. So when I do things in PD, I also have SuperCollider in the back of my head, and I've also studied other languages. And yeah, so and pure data, I think who knows what PD is, at least, and the name? Yeah, the name, okay. Who has used PD in the past? Oh, wow, okay. Quite a few people, yeah. So then maybe I can skip over that. So developed by Miller Packard since 1996. So we are approaching the 30th anniversary of PD soon, which is pretty amazing. And it's the backwards compatibility story with PD is really incredible. I mean, you can literally run patches from like 25 years ago, and they will still work as they do today. And you can even download old PD binaries on Miller's website, like Windows builds from 20 years ago, and some of them they still run. It's pretty cool. And so you can actually see how the thing evolved over time. PD comes in several flavors. There's PD Vanilla, and this is the original version. It's a really minimal core, and some people say too minimal, with a rich ecosystem of extensions called externals. And when I'm talking about PD today, I will always implicitly talk about PD Vanilla. And there has been PD extended, rest in peace. It was PD with batteries included, but it has been abandoned because it was like unmanageable. It was like too big, and there's like a big warning. Like you really have to make sure that the size of the software is in relation to the size of your own development team. In that case, and this team was basically a single person, and so it's really easy to get burned out. So watch out for that. Try to keep things small and really shift things and to extensions so that other people have to deal with them. There's Pearl-Data and like PD L2org. I would call it a spiritual successor of PD Extended, developed by Jonathan Wilkers and Bukovic. And there's Plug Data by Tim Schön. That's pretty amazing. And it's basically a wrapper around PD Vanilla with the GUI rewritten in shoes, and some externals included. And it can actually run also as a plugin in a DAW. So it can rerun PD as it is in Reaper, for example. So it's basically Max for Life for PD, if that makes sense. Right. So here's like if I would have to make like a high-level comparison of SuperCollider and PData, that would look like. So like SuperCollider is about text, and like PD is about the visual. You literally draw your signals and connect objects. SuperCollider is dynamic. So this is really an important thing. I think it's one of the biggest selling points of SuperCollider, in my opinion, that can actually create synths on the fly, and they can also change the server and the server graph on the fly without audio interruptions. That is not possible in PD. In PD, you basically your DSP graph and the whole graph is fixed, and whenever you make a single change in the signal connections, then the DSP graph has to be recomputed, which probably results in an audio dropout. So you really have to pre-allocate all your stuff, all your voices, and then have to manage those. So this was like a big revelation when I first learned SuperCollider, that you can actually say, okay, I just spawn a synth, and it's pretty amazing. SuperCollider by its nature is asynchronous. So you have really the language and the server running in different time domains, and they communicate with message passing. While PD is really a synchronous environment, and I will explain later what I mean by that. And SuperCollider uses a server client architecture, and like PD is a monolith. I mean, the GUI is a separate process, but this doesn't count in this respect. I mean, you can use PD without the GUI as well. SuperCollider has a rather fluid and loose organizational structure, I would say, to put it positively. And PD is basically Miller has the final say. So he decides in the end what gets merged. But he has a small team, and I'm part of that team. And then the license, yeah, it's also like it comes up a few times. And right, I want to talk about scheduling models, because that is like what I find really interesting, and I think a lot about. like how do you actually schedule things? Because we work in a time domain, so we want to schedule events, and they have to be transformed into sounds at some time. How do you do that? And how do you get the timing you want? Actually? So there's one option. It's called synchronous in audio callback. And these are my names, so these are not official terms. So and yeah, I think people may find better terms for these. And you have an audio thread and an audio callback, and then you have a block, and it first does all the event handling and the clock timeouts, and then computes a block worth of audio, and the same thing for the next block, etc. Yeah. So and it's very simple actually. So and you can see how it is synchronous because we literally have a single thread. There's no concurrency whatsoever. Then what I call synchronous in scheduler thread. We actually have two threads. You have your audio callback and a dedicated scheduler thread. And for example, you say, okay, your audio thread needs to compute one block of audio. What it actually does is it just it writes the input into a FIFO and gets the output from a FIFO, and that's it basically. So it does nothing. And then what happens is that this wakes up the scheduler thread, and so there are samples ready to be read and written. And so the scheduler actually does the same thing as in the other model, but like on its own thread. And then it takes the input from the FIFO and writes the output to the FIFO. So they are synced to each other, but not synchronously. And actually, the size of this FIFO is the delay setting you see in PD audio settings. So this is the size of the FIFO, and this actually adds extra latency, and we can actually buffer things. So this the big advantage of this thing is that you can say, okay, I have certain events that may take longer than one block of audio, but I have this ring buffer, so I have some extra leeway, so it can be drained, and then I can fill it up quickly again. So and the advantage is I can also do any kinds of blocking operations as long as this FIFO is large enough. And I don't ever block the audio callback actually, which can be an important thing in some environments where you have other things running on the audio callback as well. Yeah, and then it continues just. The third option is what I call asynchronous and clock-driven, for lack of a better name. And you have a scheduler thread and an audio thread. And the scheduler thread, it just basically waits for input events and does clock timeouts just in its own thing. It just it runs on some clock. It could be a system clock or like a CPU clock or whatever. But then you have your audio thread, and it does its message passing and DSP. And these two and they communicate with timestamped messages and replies. Does it look familiar? So that's basically how SuperCollider actually works, and it's asynchronous. The scheduler thread never blocks the other threads. So and then there's one model which is quite funny, which I haven't seen in a while yet, but I think it's kind of interesting. I call this an asynchronous and callback driven. You have a scheduler thread, an audio thread, and the audio thread computes one block worth of audio, and then it wakes up the scheduler thread and says, okay, hey, I've advanced time by 64 samples, for example, and then the scheduler thread wakes up, handles input events, and then increments its own logical time by that amount of samples. So it runs on a sample clock, but asynchronously, which has the advantage that you can actually do sample and accurate scheduling and even subsample accurate scheduling as long as the latency is large enough. So but the language is driven by the audio thread, so you can't actually you can't control multiple servers, for example, with one language thread. So it's really basically driven by the audio. But it's kind of an interesting model, and it would be interesting to actually implement this once. Yeah, here's like a comparison at the advantages and disadvantages. I will go rather fast for lack of time, but I try to make the slides available so you can think about these things after the talk. But basically, you see that there's no silver bullet. So every approach has its own trade-offs. And for some real examples, the first one, the synchronous callback is basically pure data with the callback scheduler, or max MSP with a scheduler in audio interrupt. And it's also, I think, how Chuck works. And the synchronous scheduler thread is pure data with the polling scheduler. It's a default. It's a default actually. Asynchronous plus clock driven is like SuperCollider. It's basically like max MSP in normal mode, but they don't really have accurate scheduling. So it's just and also computer games, because the game runs in its own clock basically, and yeah, you can't run a game from the auto callback. So this doesn't. That would be strange. Yeah, and asynchronous and the callback driven. I haven't seen an example in a while, and would be curious to know if someone actually has an example. It's a little bit about the SuperCollider server-client communication, how this actually works. So you can either send immediate server messages with the client and the server. You send a message for some time n, and the server just receives and dispatches this message like in whatever future time, and you have no idea when. So this is not good for accurate scheduling, but it's good if you want to get things like to the server as quickly as possible, like for example live input or something. If you play a MIDI keyboard, you would use that. Then there's also the timestamp server messages, OSC bundles. We actually have you schedule a message at time n plus a certain amount of latency, and the server receives this bundle and asks like, has this timestamp passed? Then that we dispatch now, and it's got a late bundle, the SuperCollider. If no, we schedule this message in future. It's basically put on a priority queue, and then when the time comes, it actually dispatches and sets the subsample offset. So the users can actually also do something with the exact scheduling time, which is important, for example, for the offset out user. And that's how that works. The client can send things back to the server. And the other way around, the server can send replies to the client, and it's also called node replies. But the client just receives them at whatever time. So we don't actually have like scheduled node replies. So this would work like this. You get the current OSC, time the logical OC time at a latency, and then send it as a bundle to the client, and the client can do the same kind of scheduling. And then you can actually schedule replies on a certain time point, because at the moment you can't really the limitations of the current model is it's not deterministic, because the language runs on its own clock, and the scheduling is fairly accurate, but it's not precise, and it's not deterministic. So every time you run SuperCollider, the output will be slightly different, at least in real-time mode. Yeah, not perfectly sample accurate, and you need to apply this additional latency to accurate scheduling. And yeah, that's a big thing. And you cannot directly control the server from within itself. So you can't, for example, create a as a response for a trigger. I mean, so what you have to do is you have to send a node reply back to the client, and then the client can create this in, but it's not timestamped. So if you just create it at whatever time this message will be received on both the client and the server, so it's totally indeterministic. Yeah, it requires this full round trip, and this is something that really bothers me, for example, because it's a thing I tend to use very often in PD. Yeah, and one thing, there's actually no client-side Eugen representation that you get out of the box. You can get, I mean, you can find the synth index, and then you can send a unit command, but it's pretty hairy to actually do this. And the Eugens in SuperCollider are actually blueprints for Eugens, and we don't get a handle to the actual Eugen in a synth graph. And the PD, everything is just an object. So you send a message, and everything is in the same C object. So it's very easy. And that's why, and I think you can imagine how this complicates the implementation of VST plugin, for example, because all the parameter changes and the notifications of parameter changes. So you always have to make this round trip. So, for example, if I change a parameter, I want to get the new string representation back, but this has to be asynchronous. So this is actually a bit of a mess. The PD scheduling model. So it's very simple, actually. So you have the event handling and the clock timeouts that lead to message passing, and then the object can actually remember when this message has been received, and the DSP function might now actually do some sample accurate stuff or subsample accurate stuff with these messages. And then the cool thing is that the DSP method can also send events. For example, if there's a trigger and you want to send a message in response, it can do that. Again, subsample accurately, but you can't do this directly in the DSP graph because it can lead to weird recursion things. So instead, you have to schedule it with a delay of one block. So there is a delay, but it's always one block, and it's fixed, and it's perfectly deterministic and subsample accurate. So this is how things work in PD. And I will demonstrate that now. I have some demos to make things exciting. Yeah, I always love demos. Like there was this and it's really great joke about the NASCAR races. So I really want to. So let's see if PD crashes. I don't think so. So what I want to show is yeah, it's a bit. What I want to show is that we have this B-line object. As it's basically a line generator, and we have this metro object. And this metro object basically just creates a regular event. Just it sends a bang, and then the V-line object can actually create a subsample accurate ramp. And here I have a comparison with a phaser object, which is an actual audio ramp generator. And if I, for example, I have a table of 4,800 samples, and if I make like a ramp over 10 milliseconds, you can see it's like the same output. If I do like 100, you see it's the same output. And yesterday's someone mentioned like Stockhausen's essay about the passing of time, where actually then there's a continuum between pulses on the control domain and the audio domain. And I think PD actually represents this continuum, because what I can do, for example, okay, I have this 100 hertz sawtooth wave. And then I can actually listen to that. Then I give a little bit of other things. Error stimulating, so there's the phase also. It's sounds also the same. If we do like, okay, but also again, it's minor. This frequency is not the same. And to give a like a very funny demo, it's like little patch I've been using. It's a MIDI file player. I wrote this little chip tune, and I can play it back on my Roland D110 emulator external and start that. Now I can other things you can do in PD. Try that in SuperCollider. You wouldn't need to send like 10,000 of messages in a second. So good luck with that. So yeah, and certain things you can do in in PD that you can't do in SuperCollider, and vice versa. So I will continue now. I have to look at the time. I'm not really sure if I'm actually how much maybe I'll change the order. That's very. I will run through that maybe rather quickly so we have time for questions also. Well, maybe I think I changed the order spontaneously. I think I will. Yeah, because it's a pretty large thing. I will do like non-real-time processing. I think I'll do that. Non-real-time processing. Who of you does non-real-time processing in SuperCollider? Who uses it? Not so many. Of those who do, who are happy with the workflow.
Great results.
Yeah, the results are nice. Okay. They can be nice. So, what's the problem? Okay, so that's how you do it in PD. I think we should switch the order. But in PD, what you actually do, you just run the same patch from the command line with the batch option, and you just have to make sure that you send a quit message in the batch after a certain amount of time, so the batch actually knows when it should close down. So it's actually, you can use the exact same patch and render a non-real-time version. This works because of this synchronous scheduling model. Yeah, and it's kind of cool, I think. And with SuperCollider, you have this generate you have to generate this list of OC bundles and pass it together with this input and output sound files. Meh, I would say. And then there's this whole thing of interactive rendering. I mean, if you have a DAW, you know, how do we do things? And the DAWs allow to render projects. So we don't need to bounce in real time, but like, do we have to close the DAW and like run it from the command line to render project? No, we have a render option would just basically stop and you can actually switch interactively between real-time mode and render mode. And it kind of simplifies the workflow, I would say. And you can do that in PD, actually. There's this fast-forward message, which basically says, okay, advance the scheduler for a certain amount of milliseconds as fast as possible. In SuperCollider, it's not possible with the current scheduler. It just doesn't work. But it could be work with this fallback-driven scheduler I mentioned. For if you think it through, you might come to the conclusion that this can be actually used to implement interactive rendering. And now I would just I will demo interactive rendering. So just see how awesome this actually is. I'll take this just like for the giggles. I would just keep this patch up. That sound alike. I just want to render 1 minute of that sound. And message says, okay, fast forward for like 60 seconds. Recording, and after 60 seconds, recording. Count the seconds now. 1, 2, 3, 4, 5, 7. Now demonstrate. We have here's our file. It's exactly 1 minute long. And that's very, very useful in my opinion. So yeah, so far for that, and then I think I'm doing fine. So there are 2 more things I want to talk about, and then we'll have some time for questions. I skipped the whole section, but I was just too optimistic. So okay. Lippity. So this is really nothing. You can use pure data as a C library. Is the repo, and it runs everywhere. Really, also on embedded devices, mobile, browser. It has lots of language wrappers actually, and it supports multiple concurrent instances, which is important for DAW plugins. And there's some plugin solutions for PD and there's Chamomile. And there's also plug data, which I've mentioned already. SuperCollider, here's like a very simple example of how you would use Lippity. You just initialize the library, you init audio, and you send the DSP one message to turn on DSP processing. You open a patch, for example, and you send a message to change the frequency of an oscillator or something you have in your patch. And then you can, for example, say, I want to compute three ticks of audio, and you can do that. And this process function, you can call that, for example, like on your audio callback, or you can also do like non-real-time rendering with that. Of course, you can just render, okay, I want to generate 1 second of audio with PD, and I just will and save it in a buffer. So this is really It's really cool, and I've been using that in my own projects, in my game pieces, in my game engine. I'm using libpd as the sound backend. libassistant, it exists actually, but it directly interacts with the audio hardware. So there's no assistant process function. So it really wants to write to the actual hardware, which is an issue, and because it means it cannot run as a plugin, except for there is a driver implementation for audio units. And the users might need to use their own audio backend or just write, or just want to do a non-written rendering in process. So you can't really do that, but I have some ideas how to do that. Like I just have to find the time to implement it, but you basically just need a plugin driver as a compile time option, and export a process function with the inputs and the output buffers and the sample tick count and the timestamp parameter, which could be an OC style ATP timestamp, but it doesn't have to actually represent an actual ATP time. It could be just like also a logical sample time. You might also maybe pass a real sample rate for rate conversion if you're running on different clocks. Yeah, but now the most interesting topic, in my opinion, is like resampling and reblocking. What's that? Reblocking means to run a subgraph at a smaller or larger block size. Resampling in this context means to run a subgraph at a lower or higher sample rate. And the overlap is also a thing, like you can run a subgraph maybe n times with a hop size of block size divided by the number of overlaps. So you can actually compute these overlapped blocks for you. Turns out you can use that to do an FFT, and that's exactly how he does actually implement FFT. Like reblocking is done with a block object inside a subbatch, and you can just say, okay, run this at block size 8. Resampling means, okay, just run this at a block size, and then also 4 times upsampling. Or I can also use, say, overlap. I want to run this at the block size of 1024 with the overlap factor of 4, and then I get this hop size of 256 samples. So let's just give like a small example of how FFT is actually done is in PD. Yeah. So turns out what you can do, for example. Raw filter graph here. How does this work? If we look inside, we see, okay, we reblock this with an overlap factor, and we take the inlet and we multiply with a Han window. Then we do a real FFT on the input, and then we get back an FFT of the same size. And then we can just use our standard math operators to manipulate the FFT, and then we can just do the inverse. So we can actually use the same operators. Turns out you can even go ahead and implement a real-time phase vocoder just with PD primitive objects. You don't need to write an external for that. So that's how you do a phase vocoder in PD. And you can't now who thinks this is cool? Nobody? Ah, okay.
It's really cool.
Yeah, Lucille. Yeah, Lucille gets it. Yeah. I think you. I mean, another question: who of you actually uses FFT in SuperCollider? Not everyone. Interesting. Why? How's the implementation like? How do you manipulate the spectrum? You need dedicated Eugens for every single operation because it operates on these buffers. So this doesn't scale well, and you're really limited by what like PVOC Eugens you have. And if you want to do something which they can't do, you basically have to write your own Eugen. So that's not particularly good option. And so then another thing I want to show. Yeah, have some little time left. Oh, I think I closed PD. Well, I can just reopen it. There's another thing. Why did I close it? So clever. Yeah. Delay lines. In PD, here's like this example batch of Miller, and I have this. Is a look. The whole batch. Who thinks this is cool?
Yeah.
Okay, a couple of you. I think this is cool, right?
Sure. Was it one sample, one block size?
One sample. One sample, yeah. Okay, so another thing. Oversampling. Just an example. You have this and this really nasty phaser. Just maybe put run this at a really high pitch, so it sounds really nasty. It's beautiful anything, right? But if we like upsample the whole thing and put an anti-aliasing filter in between, as a comparison again. So and this is how it works. You have the phaser, and then this is the filter, just like Miller, which has the like hard-coded the filter. And then you have this block size, this block object, and just run the whole thing at 16 times and the sample rate. Who thinks this is cool? Yeah. Yeah. Okay. Nice. So, how do you do that at the SuperCollider?
Oh. Use the object. Sam wrote this object. Yeah. Yeah, but you can't do it on. We're just doing individual oscillators.
Yeah. Well, so it turns out that okay, here's a similar thing in SuperCollider. So we have a delay thing. I think this is still going to check it out. Yeah. Yeah, this is the shortest you can get. The frequency of 60% at 48 kilohertz. Yeah, that's where we're stuck, right? Turns out, if you look at the documentation of SSynth, there's actually this block size option where you can actually say, okay, I want to run this at a block size of 16. Okay, higher. But maybe it also works with like one sample. Oh. Oh, yeah. Okay. Another thing, okay, we have this and this hard sync synth like this hard sync sawtooth wave and I'll put a FRAC scope that we show like I can modulate both the sync frequency and the base frequency. Then of course, without the syncing and with the syncing. the documentation actually mentions that this will produce aliasing. But it turns out, I mean, we can there's this option that there's a resample option. I mean, you can actually run this at 16 times at the sample rate, and then you put a crude anti-aliasing filter after that. It's still sound, I mean, okay, but I think it sounds better. And then here, this is how it's okay. So and you can do this with distortion, for example, and all kinds of wave shaping or wavetable oscillators. So this is, yeah. So it turns out you can do that in SuperCollider. And that's where I will finish my talk. And yes.
So the SuperCollider versions 1 and 2 were actually your first category of scheduling, which is
Right. Yeah.
So and actually Chuck is actually even another category to the left because it runs its scheduler between samples. Like I know that because it doesn't have a block size. So Chuck so I know PD runs its scheduling stuff, and then it runs all the little UGENs in their block size, right? And see, so it can remember the little UGENs can remember where events happen and do them, right?
That's the same in PD as well.
No, I mean that's what PD is doing, right?
Yeah.
But Chuck doesn't do that. Chuck is actually running this, checking the scheduler every sample.
You can do it in PD if you run everything at block size 1. So,
but two UGENs, it does. This UGEN does all its samples, and then this for a block, and this UGEN does all its samples for a block. But Chuck, it does the whole graph, one sample at a time, and checking the scheduler, you know.
So you can do scheduling between
samples.
That's.
So it can schedule something one sample.
Wow, interesting. Yeah.
Yeah.
Interesting. Okay, I didn't know that. Thanks.
Yeah.
Thanks. Other questions? Yeah.
Where can I?
Yeah.
How can I get this? How this version is better?
Yeah. So it doesn't really exist yet. Yeah. Okay.
Oh, okay.
Okay, got me. I just implemented this for the talk. So I'm really confused here. I think that one. Yeah, implement that, and it's something like okay, I've been using PD and thought okay, and this has to be possible in SuperCollider. I mean, and I talked with James, I think 2 weeks ago, and he mentioned that you could do that in SuperCollider too, right? I think you could.
Yeah, you could run subgraphs at different.
Yes, exactly. And so I just figured out a way how to do this in SuperCollider on a percent basis, and it's fully backwards compatible, fortunately, except for any extensions that use buses, which very few actually do. I think almost no extensions do this. And the VST plugin extension has an option to directly map to audio buses. So basically, how it works is that we. I mean, I can just show you here. Am I? Where's the graph? So basically, I just added some things to the graph. I added the full rate and the buff rate, and then also have an in-graph tick counter. So basically, the whole graph runs at its own sample rate or block size, and all the I/O UGENs they actually they write to buses and read to buses. These do all the reblocking and the resampling so that and the Eugen can communicate with other Eugens over the buses. The only exception is local in and local out. These really stay at the graph block size and graph sample rates, so we can do this in-graph feedback. And I will do a pull request hopefully soon. I just implemented this for the most important Eugen, so just for in and like out and replace out and local in and out. So I could demo it here, but I need to really do this for the remaining few, and then also on the server side, I also have to add this logic to the other sync creation methods. But it's basically it's just grunt work. But I will make a PR, and then hopefully this could be included in the next or after the next SuperCollider version, and then we can finally do upsampling and reblocking. Actually, I mean, there is some low-hanging fruit in SuperCollider still, so we just need people to actually pick it. And if you have this background in other environments, it often helps to find this fruit or just spot it. Yes.
Is there any way to account for the bit depth as well, or is that all handled by the audio drivers? Like if I want to change from 32.
I mean, that's a different story. Because internally, SuperCollider does everything in floats, and the bit depth is just like a thing on the audio back end when it needs to convert to So and that's an audio setting, so it doesn't have to do anything with SuperCollider itself. Yeah.
Regarding what you're saying about libcsynth.
Yes.
Only addressing the audio hardware. I mean, is it that you see the way to move forward to address?
Sorry.
Is it? Do you see a way to move forward? Are you suggesting a way to move forward there?
Yeah. So basically, what I showed there is what I want to do eventually. So it's not hard to implement. I mean, it's very basic, but I need to do it. Like have this long list of tasks in my life, and so. And the thing is, I have this stack of things and the top priority things, and then the super stuff like down there. And so maybe I might reach like one of these items, SuperCollider, that it fills up again. So that this is my. But it's kind of there. So if they're resampling, so it's there. So maybe and the next thing I want to do is actually to make lib SSynth really embeddable into applications. Yeah.
With the reblocking, resampling, would it make sense to rethink the FFT?
Yeah, that's I mean that's a good question, and the thing is, like, I don't want to give an opinion on that, but with FFT, it's the problem is that with then it would mean that you need to factor out all the FFT into a separate synth, because the resampling and reblocking really happens at the synth level. So in PD, you can just say, okay, I put this a sub batch and I just reblock the sub batch, and so it can really isolate the FFT stuff. And here, that's not really possible. So unfortunately, I think we're stuck with the current FFT model. If we for some reason do a complete redesign of SSynth, then yeah, but I think that's not going to happen. So that's just one limit. So I think we just have to live with the current implementation. But I mean, it's workable. But so there's no silver bullet, I would say. But yeah.
A quick question.
Yeah.
Does this touch the plugin interface?
No, sorry.
Does this touch the plugin interface?
No, it doesn't.
Amazing.
I mean, you have to bump the plugin API version, obviously, but
also we have to bump it.
Yeah, we have to bump it, of course, but I need to do other things actually to the plugin API. I want to add some new methods, and I want to make it extendable also. And then when we do all that, we can just do this all together and just and basically bump the plugin API version one last time.
Yeah.
And then that's it. And then we can really extend it in the future without having to break it. Yeah. Yes.
During the first part of the talk, we talked a lot about scheduling.
Yeah.
And as far as I understand, is that one of the problems SuperCollider has because of its client-server architecture, that the server is attached to the clock of the audio hardware, or the interpreter is attached to the clock of the operating system. Wouldn't it be possible to attach the interpreter to the clock of the audio hardware? Or
that's what what the last model is actually is doing. So this asynchronous callback-driven thing, and this does exactly that. Basically, it just tells the interpreter to advance time in logical sample time. But it's the drawback is of course you can only have like one server to drive the interpreter. That's exactly that.
Yeah, I also written once, like, I think this was really hacky, that I could schedule synths from within a synth. Like, passing some OSC messages.
I mean, you can do, in a Eugen, you can, and you can do that in a Eugen, and you can indeed do that. It's possible, but you have to write a Eugen for that, of course. But it can be done. It's just like you can't do this programmatically, because a Eugen only deals with kind of floats. I mean, what you could do is you could write a Eugen plugin that takes a unit command, and this unit command is an OC message, and then you could actually, but then again, you need to send this message from the client. So and you can't really, and the thing is, there's no way to actually generate an OC message like on a synth graph level from a Eugen. So just like it just outputs floats. So there's just no. And the thing is, in PD, you can directly send messages or schedule messages from your object, and like that's like a fundamental limitation, and you can't do that.
What I did was I sent an OC message from the server to myself on the stack again. And then I was scheduling based on the clock of the synth.
I mean, you can do that, but in a Eugen, right?
Yes.
Yeah. But and of course, in a Eugen, you can do anything, but it's not a general purpose solution, unfortunately. So
we can't make an OSC message from floats. We can. Why not?
Yeah. I mean, we could. I mean, you can like and you have this array of load outputs that you have a trigger output, and then you just have to arrange the floats to output the right characters, like the size of the message, and then you trigger that, and then it sends a message. Yeah, I mean, yeah.
I mean, it's twisted and evil, but you could pack a message into the NAND. Like you could use NAND tag floats and
exactly. Yeah.
Floats, so like pack a serialized binary representation of the.
I mean, the thing is actually, what I have to do is in the BSD plugin extension, I need to send strings back to the client, right? And unfortunately, all the node replies are float arrays, and so I actually have to serialize my strings as floats, and then basically pass them back as strings. That's one thing I also want to add to the plugin API, to actually send an actual OC, that we can send arbitrary OC messages and bundles from the Eugen back to the client. So we don't, yeah.
So this new async model that you were talking about for audio programming, like where the control thread is calling back to the rendering thread. Do you have more documentation about it or something? Because I'm curious about it, but as a systems designer, I would have some concerns, but I almost suspect that my concerns are because I don't understand it.
I think I probably need to write it up somewhere, but I mean, basically, it's the model is basically very similar to PD's polling scheduler. It's just like instead of exchanging audio data, you basically exchange time. So I'm pretty sure it works. So it's there's basically no reason why it shouldn't work. And it's just like it has certain limitations. Like I said, only a single server. But actually, and of course, you wouldn't really do this across processes. So it would make in this case you would run the server and the engine in process, and then you communicate with the semaphore. You know, not send like actual messages over OSC to wake up the scheduler and every block. So that would be kind of stupid, yeah. So you really need an in-process solution. I mean, you could use a different process and with a shared memory interface and a process shared semaphore, and then it could work. But I think it doesn't make sense to have this as a separate process. I mean, once you settle for a single server, that there's no reason at all to have it as a separate process. I mean, you want the IDE to be a separate process, but if the server crashes, I mean, you have to restart the project anyway. So this idea to make the language crash safe is a bit moot, because in practice you have to start your thing again anyway. So I think it's better to actually have the client and server in one process and only the IDE is a separate process, in my opinion. So that's what the internal server actually does.